Okay, this is now recording. 5035 MAA, this is tutorial number 9. This is week 9. And if I'm not mistaken, you have done deflection of beams. Now, deflection is part of the deformations. So you know that so far in the first and second year, you've done the loads and the stresses that come from internal loads. So you know that for normal force, you have elongation or contraction. And you know that for twisting load, you have shearing and angle of twist. For direct shear, you have this shearing angle. And for bending, of course, this is the last thing. For bending, you have deflection and slope. Now, bending is the most complicated of them all. Well, apart from possibly torsion of non-circular sections. Because torsion of circular sections, the sections always remain plane. So you only have to care about the angle of twist. But if the section is non-circular, say if you have a square section and you're twisting it, then you also have axial strain. So because you have a warping of the section. So you have to calculate the warping function. That's quite an advanced concept. You'll see, you probably do this in year 3 or year 4 if you go that far. Okay, so Euler-Bernoulli bending theory is an approximation. Okay, so this is not exact, and I'll tell you where the approximation comes in. This one is the Euler-Bernoulli bending theory. You know that this thing is quite good summary of the bending formula. Remember that sigma is m over I times y, and these have to do with loads and stress. So this side is what you've known so far, but now you have introduced this other side. This other side takes into account the deformation. Now, when you bend something, you are curving it. You agree with me? Possibly, yes. When you curve anything, it possesses curvature. Now, curvature is, I know it looks trivial, but it's not, because curvature is a mathematical concept that assigns a very specific quantity to any point of the deformed shape of the beam in this case. So for any curve, you can assign a radius of curvature and the curvature itself. Now, the curvature is defined as the inverse of the radius of curvature. So 1 over r, if you have a circle, the curvature of that circle is 1 over r, 1 over its radius. That's it. And this r that appears here in the bending formula is exactly the radius of curvature. So you see that sigma, that m over I is also the Young's modulus times the curvature, or divided by the radius of curvature. Curvature is spelled kappa, like the, it's the Greek letter kappa, or like the Twitch chat, if you know what I mean. And it's the inverse of the radius of curvature, and it's a specific quantity that is associated with every point. So you see x, k, this is kappa of x, means that every point along the beam has its own curvature. So every point along the beam has its own radius of curvature. Okay, so imagine this, if this is a beam under a certain load, and this is the deformed shape of the beam, we can see that at every point I can define, let's say here, I am defining a circle. That circle is called osculatory circle, and the radius of that circle is the radius of curvature at that point. Okay, so you can see the sharper is the corner, of course. So say here the radius of curvature is smaller, okay, because the osculatory circle is smaller. We can also say, after some derivation that I'm sure you have done with Said, you have derived that the curvature itself is the second derivative of the deflection of the beam, which comes from this m over ei. Okay, so 1 over r is m over EI. Do you agree with me? If you take this left-hand side and this right-hand side equal to each other, 1 over R is M over EI, basically. And of course, M changes with X. So you have a bending moment diagram. This is the bending moment diagram, M of X. This accounts for beams that change in material. So you might have a section of the beam that is made of brass, section of the beam that is made of steel, and then of course you have to take into account. You have to take it into account when you do the integration. Or the beam might change shape. So the second moment of area of the beam might also change shape as you go on, because you might have a tapered beam, or you might have 2 different beams with different sections attached to each other. Okay, so the important quantities, though, are not the curvature itself, because we have no use for it, although it's important, it's interesting, we have no use for this. What we need is to know at every point, say at this point here, what is the deflection. So V of 0 at x equals 0, what is the deflection of this shape, and what is the angle? What is the slope at this end? So as you can see, for every point, say I've taken here a generic point, you have V of x that changes. So you can see here V of x is 0 in this point, and V of x is 0 in this point. And you have a certain angle, a certain slope as well, phi of x. So of course, also every point has its own. And as you can see here, phi of x is almost 0 here, and it's almost 0 here. Where you have a maximum or a minimum, the slope is 0. That's how it works. And so you can see very easily, so curvature and slope are linked by a differential relationship. So that means that the curvature is the derivative of the slope. So you can find the slope by integrating the curvature. And you can find the deflection by integrating the slope. That's how it works. So you find these 2 quantities that are important. They all come from the curvature, and the curvature is defined by these, which are very easy to calculate because you know everything about your beam. You know the load, you know the material, and you know the shape, the geometry. Where is the approximation? What do you think? Where is the approximation here? Well, the approximation is about here. Let me say this is the approximation. Okay. So this thing in reality is this divided by the square root of 1 plus derivative squared of whatever. Okay. So this thing is when the derivative is very small, okay, then this square root tends to 1. So we can take it approximately as that. Okay, so remember, there is an approximation here. That's why we have different bending theory. This is the Euler-Bernoulli bending theory. There is the Timoshenko beam. Okay, you ever heard about it? It's a beam. It's a model that takes into account the shearing effects as well. So this one only works for slender beams, which are basically the beams we are accustomed to. Okay, the beams for which the shear forces, the shear stress is never, well, can be neglected, say. Okay, remember when we did the exercise, say, neglect shear stress, that means you can also use the Euler-Bernoulli bending theory with very good approximation. Otherwise, you'll have to resort to different models for bending. Okay, so ideally, this is how you do it. You find M of X, you find the bending moment, you know everything else, you integrate it once, you integrate it twice, and that's it. You integrate it once to find the slope everywhere, integrate it twice to find the deflection everywhere, and then you can draw it. That's it. Why is it important to know the deflection? Any idea?
Examples yesterday were,
yeah.
If you have some coordinate like length constraint that it's not going to fail, but it can hit something. Okay.
Yes, that's very good. Another thing that I can tell you, and that also ties in with dynamics that we did a few weeks ago. Remember the gears. So you have one gear and another gear. They are in contact with each other, and they have an angle of pressure. Do you agree with me? Remember that?
Yeah.
And this angle of pressure that means that the forces exchanged are in this direction. Okay? So if this is the shaft of gear 1 and this is the shaft of gear 2, as you can see, these forces have a component that is separating the shafts. If the shaft is flimsy, if it's too thin, it might not fail, but the gears separate from each other. That's not good. You want them in contact all the time. So you have to take into account everything when you design. It's not just, okay, it doesn't fail. Okay, it doesn't fail, but it doesn't work. Not only it must not fail, it must also work as intended. So you have to take into account all these deflections when required. Okay. Good. So now we have a question. Remember how we did the bending moment diagrams so far? Cut and look left, cut and look right. It was a mess, especially when you have many loads. So how many segments you require to study this beam in? 5, 6, 7, and then it takes a lot of segments, and it takes a lot of equations, a lot of calculations. So here comes Macaulay's. This guy said, okay, let's create a description of the bending moment diagram by using something that were already known at the time called singularity functions. Singularity functions are these functions here with these brackets. I'm using these brackets, but in the literature you find also in square brackets or other kind of brackets. Singularity functions exist only in a certain region. Okay? Outside of that region, the function doesn't exist. I mean, it does exist and it's 0. See, this is x minus a to the power of 1. This function here is a straight line that intercepts at minus a and slope x. So it's a 45 degrees line that intercepts at minus a. So ideally, this should be the function. But since it's enclosed in these brackets, we turned it into a singularity function. That means that this thing is the usual thing, is treated as normal if x is greater than a. So if the bracket is positive, basically. If the bracket is 0 or negative, you treat it as 0. And that's where the singularity is. You have a discontinuity in derivative here in this case. You have a cusp. So what you have is this function doesn't exist until we reach a, and then it starts existing. And remember what you do when you cut and look left. Okay, if you cut and look left, say, look at this. I cut and look left. What is the moment here? 0. There's no load. If I cut and look left, 0. There's no load. Cut and look left, 0. No load. But if I cut here and I look left, the load is now m0. So at some point at A, that load started existing. And it's constantly m0. Because if I cut and look left, there's always m0. From that point onward, I will always see the same m0. And so we say that this is minus m0, x minus a to the power of 0. Now, to the power of 0 means this is 1. It's just minus m0. It's constant. It's exactly what you would expect. Yes?
What do you mean by discontinuity?
Discontinuity means that this is discontinuous in derivative. See, at this point, the derivative on the left is 0. The derivative on the right is 1. Okay? So that's you have a singularity point. So the bending moment diagram for this beam is this. Okay? So it's positive here and there is nothing here. All right, remember this? If you cut and look left, that's always what you see. Let's see what happens here. Well, the bending moment diagram here, if you cut and look left here, you have p times x. You agree? And x is this distance here. And so this is the bending moment. This is the bending moment diagram you get. Agreed? But that means that the associated singularity function is x minus a to the power of 1, which is exactly this that we did here. See, it doesn't exist until here, but then it starts existing after a. And that's the same thing you can do for this, but now it's x minus a to the power of 2. And then the same you can do for a linearly distributed load rather than a continuously distributed load. You have, rather than a constantly distributed load, you have a linearly distributed load, a triangular load, then you have a W0 divided by 6, x minus a to the power of 3, then to the power of 4, and so on and so forth. So we can sum these all together, because when they are not required, they don't exist. So it's very, very easy now to write the bending moment expression in one go, like that. You just sum all of these, because if they live outside, if they are outside of their range of, outside of their domain, they just don't exist. And so that's very easy. So you shove them all together, and then you see whenever they exist, they contribute. Whenever they don't exist, they don't contribute. It's very easy. We have something here that we have to take into account, is that if you look at this one only works for a distributed load that starts at A and ends at the end of the beam, because there is a starting point of existence, but there is not an ending point of existence. You see, it starts here and then it goes on forever. There is no way you can say, okay, it stops here now. So in order to do that, when you have a distributed load that doesn't end at the end, when you have a distributed load that must stop existing at some point, then you have to treat this. Say, if you have this W0, which goes from here to here, so from A to B, if you write this one only, which is this, you are dealing with a distributed load that starts from here and ends at the end, because you're writing just this. If you take this, it's like this. So in order to cancel this part that you don't want, you have to create a fake distributed load that acts in the opposite direction and starts here now, starts at B, and ends at the end. So in order to treat these kind of loads, you need two terms: the original one and the one that must cancel whatever you don't need. Agreed? Good. That's it. Now we are able to find the bending moment expression for all these ones, for all these complicated beams that we are going to do right now, and also to find slope and deflection. We just have to be very careful about the integration, because integration always carries a constant of integration. So we have to look at boundary conditions or compatibility conditions. Okay, let's start. So for these ones, this is question 4 of the first tutorial sheet. For these ones, we just want to write the bending moment expression. Don't find anything else. So first of all, what's missing here? The reaction forces. So can you find the reaction forces? I'm going to write down the equations. You tell me the numbers. So for the equations, I only need two equations. It's the equation in the y direction and the equation in the z direction. And I'm going to take point A as a pole of reduction of the moments. And so I'm saying that in y, I have AY, let's call this AY, and let's call this DY. So I have AY minus 18 kilonewtons minus 12 times 6 kilonewtons plus dy. equal to 0, because this is in equilibrium. And for the moments equation, around A, I'm saying that this is, so AY doesn't give any moment about A, of course, because it's passing through A. Then we have 18 times 3, which is negative, so it's minus 18 times 3 meters. So 18 times 3 kilonewton meters of moment, minus 12 times 6 times again 3 kilonewton meters, plus dy times 8 dy. And that's also equal to 0, because this is in equilibrium. Now, can you please tell me how much is dy and how much is ay? dy will be in kilonewtons, of course, and ay will be in kilonewtons. We are using kilonewtons and meters. Sorry, can you say it louder, please?
33.75 dy.
33.75 for dy. So dy is 33.75 kilonewtons. And how much?
Is
56.25
56.25.
kilonewtons. There you go. Thank you very much. So these are the reaction forces. Now that we have these, we have to write the bending moment expression. So see, now, if you were in first year, this is a quite acceptable level of exam for the first year, 40-25 MAA mechanical science. And I would say, how many segments you need? How many segments you need here?
3.
Yeah, agreed. You need 3 segments. You need from A to B, from B to C, and from C to D. So you have to cut 3 times, you have to solve the equations 3 times, and then find the bending moment expression 3 times. It's very involved. I mean, it's convoluted. It takes a lot of time. But now I'm going to show you that with the power of this table, it's very easy to find using Macaulay's. AY, so M of X equals AY positive. See, Macaulay says that if the force goes down, it's negative. AY goes up, so it's positive. AY times X minus A to the power of 1. What is A? See, look at this table. A is where the force is applied from the start of the beam. So what is A for AY? 0. So AY, X minus 0 to the power of 1. Great. Then what do we have? The distributed load. Distributed load is minus, because it's going down. Minus 12 kilonewton per meter divided by 2 times X minus A to the power of 2. What is A here? Look at the table. What is A here? It's also 0, because it starts at the start of the beam. Okay, good. Is this all? No, because unfortunately, what we said with this term, what we said is this. Okay, and that's not correct, because it starts at the start of the beam and it ends at the end of the beam, but that's not our case. So now we have to introduce the fake load, this one, that must counteract this 12 kilonewtons per meter. And so this is 12 kilonewtons a meter as well. But now it starts at 6. Starts at 6, ends at the end. So on top of this, I have to add, and I'll do this with a different color. And you tell me if this color looks horrible on your screen as well. Plus 12 divided by 2, X minus, where does it start? At 6 meters to the power of 2. Okay? What's missing? The concentrated load, 18 kilonewtons. So which one is that? Where does it start? And what do I use? Negative or positive? Negative. Coefficient? 18. X minus what? X minus 3 to the power of 1. Nice. See, it's very easy to see what do you have to use. This is kilonewton meters, agreed? So the units of these are kilonewton meters. So this is kilonewton, and this x to the power of 1 is meters. This is 12 is kilonewton per meter, and so here you need meter squared. Okay? This is kilonewton per meter, so here you need meter squared. This is kilonewton, and so here you need meter. See, everything checks out. At the end, everything is kilonewton meters. Yeah.
So could we treat, could you scroll up a bit to the picture? So could we treat D as the starting point, set the domain to -8 to plus infinity?
Yes.
And do it from
-8 to plus infinity. What?
Well, the boundary is -8.
Yeah, you can look at the beam on the reverse. So
Yeah.
you can make your x start from here if you want.
Yeah. Oh.
And then you do exactly the same thing.
Oh, I was just thinking about.
But now it's easier because your distributed load ends at the end. Okay. And I suggest you do that. You should end up with the same m of x at the end. Okay. Of course, it's not the same m of x. It's the same plot after all, but it's not the same m of x because you're starting x with one in one. If you change the origin, of course, you change the numbers.
Yeah. At the beginning, I said that you could treat it normally and just turn. Doesn't matter.
Okay. Okay. What's left? dy. So positive or negative? Positive. Positive dy times x minus 8 to the power of 1. Problem. Look at the singularity function. It exists if x is greater than a. Look at this, x minus 8. Is x greater than 8 at any time?
No.
Never. X is never greater than 8. It's at most 8. What does it mean? That we don't care about this. There you go, done. Okay, it's always 0. Even if we have it, you add it there, but it never contributes because you're always looking left. If you're always looking left, you never take into account dy. It's exactly the same. Second? You don't need to put it in. You don't need it at all. That's all. That's it. This is the bending moment expression. Now, I'm not sure if MATLAB has these, but if MATLAB had a singularity function, we can create a singularity function in MATLAB. It's very easy. And let's see if we have some time later after the tutorial. Let's see if I can knock up a singularity function in MATLAB and plot this, do a plot of this, and see how it looks in MATLAB. Okay, very easy. Just plot the function, and it looks exactly like the bending moment diagrams, very complicated ones. Some part is parabolic, some part is linear, some part is constant, some part is 0, and it comes up automatically from this. That's why it's very, very, very powerful, Macaulay's method. It's very simple, and it's one of your favorite questions at the exam as well. Is it? Isn't it? Yeah, it is. It is because it's easy. These are 3 marks. That's it. Done. Any questions? Shall we do this? Oh, look at this. Wow. Yes. Second? The value of x, you don't find. You don't need x. This is m of x. This moment as a function of x. You choose whatever is x, and then you find No, because then you need to integrate. We'll do this later. Okay. Any questions online, Lynn? Sorry, I can't see the chat. Oh, there you go. No, I don't see any questions. Is it everything clear for you online?
Yes, I think clear.
Thank you. Thank you. Thank you. All right, so let's challenge ourselves with this one. Wow. So how many terms of Macaulay's do you see? How many Macaulay's terms? First of all, how many segments? If you would do this in a classic way, how many segments?
4.
1, 2, 3, 4. Yes. So 4 segments if you do this in the classic way. Or how many Macaulay's terms?
6. 4, 5 actually. No.
I'd say 8.
8.
8.
With the moment, and then the support, and then the force.
Yeah.
The moment, and then the support, and then the force.
And the distributed load is 2 Macaulay's terms.
Oh,
Okay.
Oh, there's the minus 10.
So you have 1, 2, 3, 4, 5, 6, 7, 8, 9. I miscounted. So it's 9 terms. You have to write 9 terms. Yes. Second. Why? No, it's not a mistake.
Why is it judgmental?
Oh yeah, well, it might be. Yeah, it doesn't matter. It's fine. Okay, so let's do this. So let's start with the easier one, which is the 5 kilonewtons load. Let's say that using Macaulay's, m of x is minus 5 x minus 0 to the power of 1 plus 10 x minus 0 to the power of 0 plus 30 x minus 2 to the power of 1 minus 7.5 x divided by 2 x minus 2 to the power of 2 plus 7.5 divided by 2 x minus 6 to the power of 2 minus, so plus here and minus here, 10 x minus 6 to the power of 1 negative 20 x minus 6 to the power of 0 plus 20 x minus 8 to the power of 1 minus 5 x minus 10 to the power of 1. Now, 10 is the greatest number here, so this last load at the end, not required. There you go, done, solved. 1 minute. Yes?
With the distributed load in the equation, do you divide by 2? Is that what the equation says?
Because if you look at this,
Yeah, it does.
okay. If it's a distributed load, it's always divided by 2. It's a constantly distributed load. If it's a linearly distributed load, it's divided by 6. And you use 10 x minus 8 to the power of 3. So, I mean, we should all be on the same page here. This is extremely easy. It's almost insultingly easy. So I will let you mull over this for 1 minute to see if you got the correct thing. And then we can move on to the real stuff. Question in the chat. Why 10 kilonewton meters is positive? Well, let's have a look. Clockwise one is negative. Sorry, counterclockwise one is classed as negative. So this is, oh, that's clockwise. Yeah, you're correct. Thank you for catching that. There you go. Thank you, Ravi. I made a mistake, and only Ravi caught it. Okay, so you're all at fault. So please check my calculations at this point because I'm not sure anymore. Are the
20 is in the other direction?
20 is in the other direction? What do you mean?
It's also a minus.
Okay, so yes, this is positive. The moment one is counterclockwise, which is negative. No, counterclockwise is negative. Wait a minute. So this is counterclockwise is negative. And so we have here clockwise. So this is positive. I was right, Ravi. What are you rambling about? And this one is counterclockwise is negative. So this is correct now. I was right. But please triple check. All right. Do you all agree with this? Are you all okay? No questions? Can we move on? Let's move on. Now let's solve for slopes and deflections using Macaulay's method on a determinate beam. Do you remember what is the difference between a determinate beam and an indeterminate beam? No? It's how it's constrained.
You've got the same amount of unknowns as equations.
In equilibrium equations. So if you can solve the reaction forces using only equilibrium equations, so in this case, if you have at most 3 unknowns, then this is a determinate beam. If you have too many constraints, so if the beam is over-constrained, you can't use just equilibrium equations. Remember what I told you last year when we said determinate beams is what we do now because we only need to solve for equilibrium equations. You only know how to do that. When we deal with indeterminate problems, we need to take into account the deformations. And that's what we are doing now. We start with solving determinate beams, and then we're going to solve an indeterminate beam by making use of the fact that we know how to calculate the deformations, and we know that at the constraints, those deformations are 0. Some of them. Okay, so let's do this. A cantilever beam used to support a uniformly distributed load between B and C. Assume the Young's modulus of elasticity is 200 gigapascal. Find the deflection and the slope at the free end, C. Appropriate engineering units. First of all, we need the bending moment diagram of this thing. Remember, the equations are, first, you calculate kappa, and kappa is minus m over x over e of x I of x. And then to find the slope, you integrate kappa. And then to find the deflection, you integrate the slope. These are the equations, basically. And so let's crack this. So we have E. Now E over X, this is E is all the way across. So this is constant. I is also constant because this section is constant everywhere. So these two are constant. So that's very easy. That means they can go outside of the integration sign. But this one we have to find. How do we find m of x? Using Macaulay's method. That's why we studied it in the first place, to make our lives easier. So first of all, equilibrium equations to find the reactions. How many reactions you have here? 3. of course, the horizontal reaction is 0 because there is no horizontal action. So I will only use two equations. The y direction and the z, again, around A. In the y, let's say that my reaction forces are AY and MA. Let's say that MA goes in the opposite direction. And so I have that AY minus 720 times 2 equals 0. Easy. And MA minus 720 times 2 applied here in the middle. So this is 1 meter away, which is 3 meters away from A, equals 0. Also very easy. So this is the equivalent force, which is 720 times 2. So this gives AY 1440 newtons, and MA is 3600. Is this true?
No.
No?
4,320.
Yes, this is more likely. 4,000?
320.
There you go. Because it's 1440 times 3. Basically, that's what it is. All right. Now that we have these values, we can go on and find the bending moment diagram. So find the bending moment diagram using Macaulay's. Find M of x. Using Macaulay's method. And so we have MA, which is counterclockwise, so it's negative. So M of x is minus MA times x minus 0 to the power of 0.
So are you taking clockwise because?
Because that's what the table says.
For your convention, is your convention clockwise?
Yeah, yes.
Okay.
So x minus 0 to the power of 0. And then we have AY, so plus AY, x minus 0 to the power of 1. And then we have minus 720 divided by 2, x minus 2 to the power of 2. There you go, done. We don't need anything else because that's what it is. I might also want to find what is I, what is the second moment of area of this. Remember, we need I. We have M of x, we have E, we need I. What is the second moment of area of this? So 36 times 100 cubed divided by 12. How much is this? In millimeter to the power of 4?
3.
Second.
Well, I've converted it to millimeters. Or
360.
and I got 3 times 10 to the minus 6.
I'll do it myself. It's 336 times 100 to the power of 3. Divided by 12. It's 3 million. So it's 3 times 10 to the power of 6 millimeters to the power of 4. Okay? It's constant everywhere. So it does not depend on x. And so now we find the deflection. So to find the slope, we integrate kappa of x. And so to integrate kappa of x, we say that phi of x, remember this is phi of x, equals 1 over EI. So remember, it's m of x. It's minus mx. It's this. Okay? So E and I go outside of the integral sign. The negative will just change sign to everything. And so I can integrate this by saying, now, one thing I forgot to tell you about the singularity functions, that integrating them is extremely easy. So the integral of x minus 0 to the power of 0 is x minus 0 to the power of 1 divided by 1. The integral of x minus 2 to the power of 2 is x minus 2 to the power of 3 divided by 3. Okay, very easy. They integrate exactly like polynomials. And that's what's powerful. So I'll say that this times ma x minus 0 to the power of 1 divided by 1 plus ay x minus 0 to the power of 2 divided by 2. Sorry, this is positive, negative, positive, negative, positive. 720 divided by 2 times x minus 2 to the power of 3 divided by 3. Plus C1. What is C1? Constant of integration. This C1 is also called phi 0. Because it's the initial slope. Okay? And of course, I can already tell you that C1 is 0 in this case. How do I know? Because the slope here, it's constant, is fixed. So there is no slope at point A. So I know that this slope must be 0. So phi 0 is 0. Well, we'll find this later, but I can anticipate this to you already. So let's find, so let me turn this red. And now we integrate once more for the deflection v of x. So v of x is 1 over EI. Integrating this is MA divided by 2 x minus 0 squared minus AY divided by 6 x minus 0 to the power of 3 plus 720 divided by 6 times 4 is 24 x minus 2 to the power of 4 plus C1x plus C2. You agree with me? That's it. Now, if you plot this in MATLAB, if you plot this, you will see the deformed shape of the beam. It's very important, very nice. You see exactly the deformed shape of the beam if you plot that. But you can't plot this because you don't know how much is C1 and you don't know how much is C2. C2 is also called V0 because it's the initial slope. And so, of course, we also know that since we have a fixed support on the left-hand side, the initial slope is also 0. But now let's find it formally. To find this formally, let's apply boundary conditions or compatibility conditions called compatibility equations. What are the boundary conditions here? We know that the deflection at 0 is 0 and the slope at 0 is 0. So when x equals 0, v of 0 is 0 and phi of 0 is 0. Agreed? Let's do this. So equation 1, we have fix in A and fix in A, the first equation says that V of 0 is 0, and the second equation tells that phi of 0 is 0. Let's do them in the other way around, which is easier, and I'll show you why. So for phi of 0 equals 0, what is phi of x? Phi of x is this beast. Okay? So is this beast, but let's say that we want phi of 0. So this is MA times 0 minus 0. So this goes away. AY times 0 minus 0. This goes away. 720 divided by 6 times 0 minus 2 to the power of 3. But this is a singularity function. So 0 minus 2 is negative. And if it's negative, it's 0. So this also goes away. So we are left that phi of 0 is C1 divided by EI. But it's also 0. This thing is C1 divided by EI. And that means that C1 is 0. Exactly as I said earlier. Agreed? Agreed. Let's do V0. Well, this is 0. 0 minus 0 goes away. 0 minus 0 goes away. 0 minus 2, negative, goes away. C1 times 0 is 0. So C2 divided by EI. This thing is C2 divided by EI. And so that also means that this is equal to C2 divided by EI. So that means C2 is 0. And there you go. We have found that C1 and C2 are 0. And now we can plot this in MATLAB and find V of x, exactly the deformed shape. We'll see if we have a bit of time later, we'll do this later. Okay? Questions? Questions, and then I'll give you a break. I have one question in the chat. Oh, Asia said 4320. Let me check if this is correct. Yes, 4320. Thank you, Asia. Yes. It's not usually 0. So I can tell you that if you have a fixed support at the left-hand side, C1 and C2 are always 0. If you don't have a fixed support at the left-hand side, let's say if you have a roller or if you have a pin at the left-hand side, C2 is always 0, C1 is always non-zero. Okay? C2 is always 0 if you have a support here. But if you have a support not at the start, neither C1 nor C2 will be 0. So you have to calculate that. Okay? That's why they are called phi 0 and V0, because it's the slope at 0 and the deflection at 0. That's what it is. Yeah.
So in the material properties, the I can be either step function or normal ones.
Yeah.
Pretty easily. But for E, for the material, well,
it can only be a step function.
It can only be a step function.
Of course.
And then we treat it the same as with this like double function.
Yeah, in that case, since it's an integration, you can split the integral into separate bits from 0 to 3 and from 3 to whatever. Because in that case, E is constant from 0 to 3, say, and then it's constant again, but a different constant from 3 to 6. Okay? Yes?
Go up to question 6, please.
Question 6.
Yeah.
Yes. Okay.
No, not that one.
Which question 6? This is question 3. Oh, this one.
Yeah.
Okay, so if you are happy, I will go through this question 6 very rapidly. And then we'll solve, well, then we'll have a break. Yes. Yes. Why is not in the picture? It's uploaded on all of them. Oh, okay. Sorry, this one. Okay, this one and this one we'll do later. So this one is question 6. This it tells you which beam it is, so you have to draw it yourself. It's a simply supported beam AB. So simply supported means pinned and roller. And in this case, it doesn't matter which one is the pin and which one is the roller, because it only affects the horizontal reactions, which in this case you don't have. There's a length of 8 meters. Carries a concentrated load of 20 kilonewtons 2 meters from A. And a uniformly distributed load of 5 kilonewtons per meter over the length from the midspan to B. So 1, 2, 3, 4, 5, 6. Of course, it's 11. This is 2 meters. And this is 1, 2, 3, 4, 5, 6. Five kilonewtons per meter. We also know that EI is 20 meganewton meter squared. So this EI is already given. We don't give you E or I, we give you EI altogether. So use Macaulay's method to obtain the deflection at midspan. So what do we want here? What is the answer, the final answer that we want? We want V of 4. So we want to find how much is V of 4. Agreed? It's the deflection at midspan. Again, don't let me do this alone. So this AY minus 20 minus 5 times 4 equal, sorry, plus BY equals 0. And this is minus 20 times 2 minus 5 times 4 times, this is applied here, which is 6 meters away. Plus BY times 8 equals 0. So can you please tell me how much is BY and how much is AY? So BY is 40 plus 120, no, yes. It's 160 divided by 8, which is 20. So BY is 20. Do you agree with me? So AY is 40 minus 20 is 20. What? Yeah. Yeah, of course, it makes sense because it's the same for equilibrium. For equilibrium, this thing is equivalent to a 20 kilonewton force applied here, which is exactly a symmetric beam in this case. So you have 20 on A and 20 on B. So this makes sense. Okay, now that we know this, we find the moment, find m of x, Macaulay's. So we have m of x is ay x minus 0 to the power of 1 minus 20 x minus z is 2 to the power of 1 minus 5 divided by 2 x minus 4 to the power of 2. And that's it. Because by is at the end of the beam, we don't need it. Is m of x, integrate for the slope. So phi of x is 1 over ei times the integral of this with the sign or changed. So it's minus ay divided by 2 x minus 0 to the power of 2 plus 20 divided by 2 x minus 2 to the power of 2 and plus 5 over 6 x minus 4 to the power of 3 plus c1. Easy. Integrate again for the deflection. Integrate again for the deflection. V of x. And we have that V of x is 1 over ei. See how fast you can solve this exam question? Extremely fast. If you practice this, you're gonna zip through the exam. Plus 20 divided by 6, x minus 2 to the power of 3, plus 5 divided by 24, x minus 4 to the power of 4, plus c1x plus c2. Compatibility equations. Now, these are the interesting ones. Compatibility equation is that what do you know about the deflections of this thing or the slopes? We can't say anything about the slopes. Because see, if I draw the deflected shape, might look like this. So what do you know about the slopes? Nothing. There is some slope here and some slope here. So I can't tell anything about the slope. But I know that there is no deflection here and no deflection here. So I say that V of 0 is 0. So the compatibility equations are pin in A and roller, let's say another pin in B. It doesn't matter, even if it's a roller, it's still the same thing as a pin in the vertical direction. And we have that V of 0 is 0 and V of 8 is 0. So it's 0 at the start and the end of the beam. Agreed? So this means that C2 is 0. How do I know? Because V0 is C2. We did this. It's exactly what we did last time. But this one is now more complicated because I have to put 8 here. So this gives the equation that tells me 1 over ei times minus ay divided by 6, 8 cubed, plus 20 divided by 6, 6 cubed, plus 5 over 24. 8 minus 4 is 4 to the power of 4, plus C1 times 8. And that's equal to 0. Now this equation here, you can solve for C1. Okay, C1 is the only unknown here. And so solve for C1. And finally, V of 4. Now that we know C1 and C2, you go here and say V of 4 is this applies, this is 0. So V of 4 is 1 over EI minus AY divided by 6 times 4 to the power of 3 plus 20 divided by 6 times 2 to the power of 3. This is nothing, plus whatever you get from C1 times 4 plus 0. Any questions? Okay, let's have a break. 5 minutes. Yes. Just a second, let me check the chat. Nothing in the chat. Yes. I don't know. I didn't solve it. But yeah, if you solve this, again? 116. Is it millimeters? What is it? Meters, millimeters? What is it? So check the units.
So you may just want to
Here, where? This.
Maybe it's the guidance will find the truth. Fix the hole. Maybe. Yeah, nobody ever came. But that was completely separate. It had nothing to do with anything. Yeah. We didn't know about it.
So that's from what
And you get
No, there's keep that other new culture exchange, what like his methods where
All right, let's resume. So now we deal with an indeterminate beam, our very first indeterminate beam. How do I know it's indeterminate? Yeah, so it's too many reaction forces. So how many reaction forces you see here? I have three from the fixed support, 2 from the pin, another 2 from the pin, are 7 reactions, but we only have 3 equilibrium equations. Now, the horizontal equilibrium equation is also useless because there are no horizontal actions. So the 3 horizontal reactions are 0, but we still have too many unknowns for 2 equations. Let me spell out the equations here. Equilibrium equations. So we have 1 along the y-axis, 1 along the z-axis around A. And so this is, let's say that these ones are AY, MA, BY, and CY. And so I have AY minus 10, minus 6 times 3, minus 15, and plus BY plus CY equals 0. Agreed? And here we also have MA minus 10 times 1 minus 6 times 3 times, it's applied here, and say it's 2 and 1.5, it's 3.5. Do you agree? 3.5. Minus, so plus 2by plus 3cy minus 15 times, it's not 3, this is 5 to cy, 15 times 5 again, and then minus 9. Okay, so how many unknowns we have here? 1, 2, 3, 4. This is the second unknown, this is the third unknown. So we have 4 unknowns. 4 unknowns. Ouch. And only 2 equations. So I'm going to call this one equation 1. And I'm going to call this one equation 2. Does it mean that we stop here? Of course not. Of course not. Because what happens now is that it's true that we have only 2 equilibrium equations, but how many compatibility equations we have?
2 more.
How many compatibility equations we have? Look,
3.
is it 3?
This one and 2 more.
No. No, it's not that easy. Just answer my question. How many compatibility equations we have? How many boundary conditions you see?
Oh, 3. I mean, 3 supports. So
3 supports, so how many equations?
3.
No.
Well, the first one is moment, and then
Yes.
and then
So you have 2 compatibility equations here, 1 here, and 1 here. So it's 4 compatibility equations. Wait a minute. So we have 4 compatibility equations. So do we have 6 equations and 4 unknowns? No. We have 2 more unknowns. What are they? C1 and C2.
Oh, yeah.
Okay, don't forget, we only have C1 and C2 as unknown. So compatibility equations fix in A, pin in B, pin in C, fix in A means phi of 0 is 0, V of 0 is 0, V of 2 is 0, and V of 5 is 0. You look puzzled.
Why don't the supports at the bottom get unknown?
Second, what?
Why do they only constrain it in deflection and not in angle?
Because a pin does allow for slope. Because the beam can rotate around this. See, if I try to draw the deflected shape of this beam, it looks like this. Okay? And as you can see, there might be slope here. Huh? It's best if you look at it here. See, pins do allow for slope. Okay?
Sir,
Yes.
what's a compatibility equation?
It's the boundary conditions. You have 1 compatibility equation per reaction force.
Okay.
So every reaction force gives you a compatibility equation. Okay, so here you have 2 reaction forces. So you have 2. One is a moment, so the compatibility equation is on the slope. One is a force, so compatibility equation is on the deflection. Force, 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 deflection, deflection, deflection. Moment, slope. Okay. So let's recap. This is equation 3, equation 4, equation 5, equation 6. 6 equation and only 4 unknowns. No, we don't have 4 unknowns because inside here we also have C1 and C2, which are 2 unknowns. Okay, so we have 6 equations and 6 unknowns in the end. We can solve it, and that's what's important. Now we just have to solve it. We know we can, it's possible, so let's do it. Oops. So you know what? Let me take these ones here and make them smaller a bit. Because now that we, okay. First of all, of course, since we don't have values here, we're going to take the unknowns with us. When we write the bending moment equation, the bending moment diagram, those are unknowns. So you just have to carry all the unknowns with you. That's how it works. So bending moment diagram, M of x is Well, MA, so this is counterclockwise, so it's negative, MA x minus 0 to the power of 0 plus AY x minus 0 to the power of 1 minus 10 x minus 1 to the power of 1 minus, so let's do by first, so plus by x minus 2 to the power of 1 minus 6 divided by 2 x minus 2 to the power of 2, and then this doesn't end here, doesn't end at the end, so we have to use the fake load as well. Do this in this strange color, plus 6 divided by 2 x minus 5 to the power of 2, and then we have negative 15 x minus 5 to the power of 1, positive cy x minus 5 to the power of 1, and finally 9. Do we use it or not? This 9 kilonewton meters. It's x minus 0 to the power of 0. Sorry, x minus 3, 5, 6, x minus 6 to the power of 0. What do you think? It will always be 0.
I'm looking at it, it looks like we should use it, but I don't think we need to. It's always, I mean,
It's on the end, so you don't need it. Because it's x minus 6 to the power of 0. So yes, Marius is also, I think he said so. Yes, no, it's on the end, yes. So we don't need that because it will always be something minus 6 to the power of 0, and it will never, power of 0, when you integrate it, will be to the power of 1, integrated will be to the power of 2, but it's always x minus 6. It's always useless. So this is a quite long expression for the bending moment. Let's integrate this for the slope. And so we have MA x minus 0 to the power of 1 plus AY x minus 0 to the power of 2 divided by 2 minus 10 divided by 2 x minus 1 to the power of 2 plus by divided by 2 x minus 2 to the power of 2. Sorry, this is plus, these signs should not be changed. So negative, positive, positive, negative, negative, positive, and positive, negative. So this is plus 6 divided by 6 x minus 2 to the power of 3, negative 6 divided by 6 x minus 5 to the power of 3, plus 15 x minus 5 to the power of 2 divided by 2, minus cy x minus 5 to the power of 2 divided by 2 plus c1. This one is the slope expression. And then we have the deflection expression. Yeah. Because we have to change the sign. See, the equation is that you need to integrate minus this. So this is 1 over EI times MA divided by 2 x minus 0 to the power of 2 minus AY divided by 6 x minus 0 to the power of 3 plus 10 divided by 6 x minus 1 to the power of 3 minus by divided by 6 x minus 2 to the power of 3 plus 6 divided by 24, x minus 2 to the power of 4, minus 6 divided by 24, x minus 5 to the power of 4, plus 15 divided by 6, x minus 5 to the power of 3, minus cy divided by 2, x minus 5 to the power of 3. This is not 2, this is 6. And plus c1x plus c2. This beast here. Let me do this better. Now, do you all agree with me? And now, look, this equation here tells you that C1 is 0. Do you agree? Look, 0, 0, 0 minus 1, negative, 0, negative, 0, negative, 0, negative, 0, negative, 0, negative, 0, C1 is 0. This one tells you that C2 is 0. Negative, sorry, 0, 0, negative, 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 0. So C2 is 0. And these two are the two equations you need to solve for the other two unknowns. So if you do V of 2, let me just do V of 2. So for V of 2, V of 2 is 1 over EI times MA divided by 2 times 2 squared minus AY over 6 2 cubed plus 10 divided by 6 1 cubed. So this is not required. Minus BY divided by 6. No, this is 0. So from here on, everything is 0. 0, 0, negative, negative, negative. Then this is CY is 0. C1 is 0. C2 is 0. So this is it. This one equals 0. This is the equation. This is equation 4. Sorry, equation 5. Agreed? If you look at this, this is equation 5. And then you can find the same for equation 6, which is just V of 5, which is equal to 1 over EI times MA divided by 2 times 5 squared minus AY divided by 6 times 5 cubed plus 10 divided by 6 times 4 cubed minus BY divided by 6 times 3 cubed plus 6/24 of 3 to the power of 4, and that's it. Everything else is 0. This is equation 6. So see, we solve the system. So from here we said that C1 is 0. From here we said that C1 equals 0 and C2 equals 0. So we have used 6 equations and 6 unknowns. We were very lucky that these are not all coupled. Only equations 1, 2, 5, and 6 are coupled together. So these are a system of 4 equations in 4 unknowns plus 2 separate equations in 1 unknown. All right? Good? Nice. That's it. So the hardest you can get is many terms that you have to integrate many times, but it's just it's clerical work at this point, because it's not anything you have to think about. Yes, scroll down. Yes. Any questions? We check online. Can I see the last equation? Oh, there you go. And I've done this very fast, so please triple check my calculations, okay? Because I don't trust them. Yes. Again? Okay. That's it. Yes. Just a second. Let me. I missed equal to 0 here, because otherwise it's not an equation. Yes. Yes. Up. Up here.
Put 0 in
Yeah.
C1.
Yeah.
Here you put 0 in
Different C2. Yes.
And then why are you putting 2 and 5?
Because you have 4 unknowns here and only 2 equations. So this equation and this equation, which give you these ones, with these two you can solve this, and this. You can solve the system for all 4 elements. All right, I think we have one last things to solve, which is quite easy, no? I mean, you can do this yourselves. It's quite easy. Let me draw it. So uniform simply supported beam. Span of 5 from A. For me, that's for me. Now, this one is quite particular because it's asking what is the position of maximum deflection and what is its value. How do you find that?
Well, the maximum position is the first derivative,
Yes, so where is the maximum deflection?
where it's 0.
What is 0?
So this is the first derivative.
And what is the first derivative?
Sorry, after we integrate once, this has to be 0.
Okay, so the slope.
Yeah.
So what we are saying, to find the maximum load, to find the maximum deflection, you need to know
Not in this
phi of
this
x
example, but
equal to 0.
here you should also check the domain limit.
Yeah, of course.
Clearly not.
Okay, so where phi of x is 0, the deflection is maximum because the slope is the derivative of the deflection. And so you find maxima and minima to use the derivative of the function, set it equal to 0 to find the critical points. Solve for x. Xc. Finally, V of Xc is Vmax or Vmin. Okay, very easy. So this is your critical point. That's it, done, easy. Okay, so I will not do this. You will do this very easily. Now let me check if I can. If we have MATLAB here, I want to see if we can do this. No, we don't have MATLAB here. That's it, done, solved.
I mean, there's no line.
Can I use MATLAB online?
Yeah, you can.
Where? On MathWorks.
Yeah. Yeah.
Check. Oh, I'll need to log in. Let me see if I can do this with Wolfram Alpha. That would be very easy.
Probably can do it in Desmos.
Yes, with Desmos we can do that
But I
as well.
don't know how to set the domain. But it for sure looks nicer.
Can we? Does Wolfram Alpha has singularity function? Singularity is a movie. Okay, that's a good one. Let's say singularity. Find singularities, visualize singularities. Let's say piecewise functions.
Desmos, the domain is the funny bracket. I think it's easier.
Okay, so it's something like this. Okay, let me check one of the simplest ones we found. Say this one. I'm going to try and solve for this one here, which only contains one singularity function because x minus 0 to the power of 0 is just 1. So this is minus MA, and MA was 14 minus 4320 plus 1440 times x minus 720 divided by 2 times, so we want the piecewise here, times piecewise piecewise, and this is x minus 2 squared if x is greater than 2, and 0 if x is smaller than 0. Sorry, x is smaller or equal to 2. Smaller or equal to 2. This is smaller or equal than 2. Why doesn't this work?
You have to put it 0 in the colorful square.
Yeah, this is 0. What is this? Should be x smaller or equal than 2. But why doesn't it work? Does it work? Oh yes, it works. There you go. This is the bending moment diagram. And so plot this from 0 to 4. Zero to 4. Yep. This is the bending moment diagram. See? And this is the bending moment diagram for this beam. Shall we look at the deflection? So let's find the deflection of this beam. So I can just write down this one with the singularity functions, which now I know how to use on Wolfram Alpha. I just learned with you. It's very good. So of course, I'm not saying EI, so we also need EI. And E is 200 gigapascal, so this one, 1 over EI. E is 203 times 3E6 times this is x minus the x squared times this one is changed sign, x squared times x squared minus this, which is a divided by 6. No, this is divided by 2. This one is divided by 6 and is x cubed. And this is 720 divided by 24, x minus 2 divided by 24, x plus 2 divided by 4.
Are you sure that it's to the power of 24?
No. In fact, this is very bad. Power of 4. There you go. This is the deflected shape of this beam. See? And as you can see from the plot, it has 0 deflection and 0 slope at the start. That is exactly what we were expecting. Okay? So I suggest you play around with this. You can also write a MATLAB code to explore it a bit and see how increasing load change the deflection of the beam. Okay, we got any questions online? No, thank you. Yes. Second? Which example? The last one. This. So if you don't have any more questions, let me stop recording, and thank you very much.